Good evening, my name's Graeme Smith. I'm the Chief Executive of Oxbotica. I was asked to come and talk a little bit about some of the technology that we have in some of our autonomous vehicles, and particularly to talk about the sort of complex urban environments that Lola was describing earlier. Let me just explain a little bit about who Oxbotica is, in case you haven't heard of us. We're a small company based in Oxford, and we spun out of Oxford University about 3 years ago. So we were an AI and algorithmic software development company working mainly in the area of mobile robotics. So this is one of our cars we've developed with Greenwich or rather Canary Wharf as a backdrop. This is a little car we made just to help us prototype some of the software that we're currently running as part of the Gateway project. We had this car up and running last year, I think, Nick, it was, and we demonstrated it I think just about a year ago, running around the peninsula. So this is it running now in our test track in Culham in South Oxfordshire, and it really does go that fast. It's a nice, neat little demonstration car, and as you'll see here, Emily is driving it with her hands off the wheel. And one of the things we really found difficult when we're trying to video drive this car is to prove that they're driverless. So you'll see all of our cars, people are waving their hands around here and say, "I surrender." So this is the sort of thing that we do. No, we've currently been focusing very much on sort of urban environments, pedestrianised environments. So the work that I'll talk about shortly in Greenwich has been on cycle paths and low-density traffic environments. We have quite a family of autonomous vehicles in Oxbotica. You've seen our little blue genie in the middle there, but we've got we have off-road vehicles. We've had some demonstrations in Milton Keynes. With the university, we've been running a Nissan Leaf in Oxford for 4 years now. That's the UK's first autonomous vehicle. It's been running since 2012, I think now. Harry the Gateway Pod that Rama showed already, and we've even been around a racetrack on it. So your petrol heads can maybe come and try that one as well, Rama, for us. So these are our autonomous solutions. Oh, top right as well is a commercial cargo delivering vehicle that we're developing for Greenwich as well. Our approach to all these vehicles is that they're all trying to tackle the same problem. The technology is the same for all the vehicles, and our software is really the same stack for all these different vehicles, just tailored to very specific environments. So the type of environment we've been running in as a preparation for Greenwich, these are some demonstrations. Top right is Milton Keynes. This is maybe familiar to some of you. Bottom right is one of our first runs in Greenwich last year. And this bottom left, Sky News again, acing everybody else. They came to see us in Milton Keynes and brought a helicopter with them. So occasionally you'll be able to see the exact sort of environment that these vehicles are running around in. So for us, this is a sort of a typical urban environment. You can see here, we're mixing with people. We're mixing with cyclists when we're in Greenwich. We find cats and dogs, all sorts of things. So this is a very different problem than you might find on a public road or a public motorway. This is more shots of Harry the Pod. Bottom right gives you some of the idea of the sort of testing that we do in a private environment before we take the pods out on the street. So initially we use objects like the big rubber balls to roll in front of the vehicle. Then we use disposable employees like project managers, and then we go up to software engineers, and then I get to test it. So you'll see here. I think this is some pictures from our press day when we launched Harry just last month before the trial started. There's the sort of display that the operator might see inside the vehicle. So for these vehicles in Greenwich, we always have a safety steward inside the vehicle. It's part of the code of practice that Nick talked about. And you'll even see that Google, who've driven 2 million miles in the US, they'll always have an operator in the vehicle at all times. The purpose of that person is just to resume control if there's ever an issue with a vehicle or an accident. So while we're talking about Greenwich, this is another vehicle that we're developing for Greenwich. Or for Gateway rather. It's a low-speed commercial delivery vehicle. We have developed this with some design guidance from Ocado. And on the back of this vehicle, there's a number of different hatches that have PIN codes on or near-field communication device, so you can open it with your iPhone. So the idea is that this might come and park up in your vicinity, and when you get home from work, you'll dial it up on your iPhone, and it will come to your front door. You can take your shopping out, it will go and park up again and wait for the next person. So that's one potential use case. The second one is it sort of follows the delivery person down the street, a bit like the milkman model, that the delivery man will go to the front door and then the vehicle will go off and park itself or wait up for him to come out again. So this vehicle will be in trials probably from the end of May onwards, either in Greenwich or maybe even in Royal Arsenal. Still trying to work through the final details. So in terms of what I was asked to speak about, so what is it that's different for us about sort of complex urban environments? What is it that's different from roads? And typically we find that the environments that we work in are unmapped. You've probably all got navigation systems in cars, or you've experienced them. For autonomous vehicles, there's a lot of companies right now mapping the world in 3D. But the areas that we work in, which can be in places like Greenwich, on public footpaths, we also work in shopping centres. We have some projects going off-road vehicles. We have projects with mines. We have projects that are underground. Really, none of these environments are mapped for us, and that's a very different proposition to some of the vehicles that you might have seen in the US. Also in urban environments, we find out that GPS is very unreliable. So if you're in a field in the middle of nowhere, GPS can be quite reliable. If you're in an urban canyon in a city, or you're inside a shopping centre, then GPS is not really reliable enough to help you guide a vehicle. We often find in sort of urban environments, there's a big mixture of sort of indoors and outdoors. So you can conceive in Milton Keynes, for example, an application where a vehicle might start off by the station. It might actually run right through the shopping centre. And why shouldn't it? We work a lot moving between roads and pavements. So again, in Greenwich, we use the cycle path. In Milton Keynes, we use the network of public footpaths there. And occasionally we'll go on the road as well. So it's a very different use case when you're hopping between one and the other. I've mentioned pedestrians, cyclists, cats and dogs. They're a very strange combination we get. And what we also find as we start to look at how do you have more than one vehicle coexist in the same place is that you need some way of coordinating between vehicles. You need the vehicles to be able to talk to each other, exchange information on mapping, on obstacles that you've seen, on obstructions on the route. And that's quite a complex task in a tight environment, which brings us on to the need to maybe start to integrate with other forms of transportation system. So a lot of people are seeing these urban type of vehicles as being part of the last mile or the first mile of the transportation problem. So they definitely need to integrate with other transport hubs. So in terms of some of the technology that I said I'd talk about, how do you build an autonomy system? So what I'm going to do now is run really quickly through some of the tech and show lots of videos about some of our tech working. But really, there are only three questions that we have to ask about how do you make autonomy work. So the three questions is, where am I in the world? So geographically, where am I? What's around me? Is it roads? Is it cats and dogs? Is it footpaths? Is it people? And then what do I do next? So it's quite a simple subset of problems, and the answers are even easier. There's only two answers. If you're driving a car, you can either go faster or slower, or you can go left or righter. Quite a simple control problem, right? Why do we make it so complicated? So let's talk about the first one of those, mapping. So here's some maps. These are some 3D laser maps that we created from some of our vehicles. This is one way of mapping. We have other ways of mapping I'll talk about later. So top left is Milton Keynes, top right is Oxford. Bottom right is here, I think. You might recognize some of these buildings. This is the University of Greenwich in full Technicolor in 3D. And we can also use the same technology to map indoor environments. So for example, this one here is a warehouse. So we use the same tech to help us map in 3D exactly where things are. And then we can use that to help us localize, navigate around certain areas. So this is one technique. This is us using that sort of information. So rather than just showing a 3D model here, what we're showing is a lot of mathematics that are helping us localize a vehicle in a specific place. So we're using the 3D model we created previously, and we can figure out where we are within that, and then where do we go from there. But we also can localize using vision. So one of Oxbotica's competencies is around low-cost vision systems. So the laser systems I showed probably cost about £5,000 to £10,000 each. Some of the higher-end laser systems you'll see on top of the Google cars are about £70,000 each. So we work a lot with low-cost cameras, and this is one of our low-cost localization techniques. So what we're doing here is on the left-hand side, you can see a live feed from a video, and on the right-hand side is a previous experience of being in the same place. And all those colored lines you can see is just the system figuring out where it is and trying to compare that to a previous memory of being in the same place. And the techniques we've implemented are really quite robust. So if you're using vision to localize, you've got to remember it's like dark half of the time. You have different seasons, you have snow, you have rain, you have sunshine. You've got to be able to localize very robustly in lots of different conditions. So you can see here, if we just start again. So on the left, we're localizing the day against a memory of being in the same place at night. It's kind of a hard feat, but we've got that one down to a pat now. Here we're localizing on a really sunny day with lots of shadows against a memory of being in the same place on quite an overcast day. Here we are, this is the day it snowed in Oxford on the left, and we're localizing against like a day with a sunny experience. So we can use the same sort of localization technology, anywhere, like underground, in shopping centers. It's our primary way of localizing in Greenwich as well. We do use lasers as well, so we use lasers for what we call perception. So perception is really what's around me. And if you've never seen one before, this is sort of what a laser or a scanning laser map looks like around the car. So you can see here, this is a stationary vehicle. You might be able to see people walking around it, cyclists. It's probably not as well defined as you might have imagined it would be, but this is what the car can see. When we're trying to detect pedestrians, this is the kind of resolution we get from this type of system. And what we do with that is we take that basic information, we have lots of clever software, and it turns it into this type of view. So what we're doing here is this is probably the same data set. What we're doing here is we're tracking things that are moving. We're not quite sure always what these things are, but we can track discrete things that exist around us and where they're moving and how they're moving. So these little trails behind the objects are just some sort of transient trail showing where they've been. And you'll see in each of these objects there's like a lightsaber coming out in front of it, which is like an indication of trajectory. So that helps us figure out in which direction people are traveling and what their intention is. So this is kind of low-level processing. This is what we call model-free classification. So we haven't actually modeled what the things around us are, but we just know that there are things there. We do have some model-based classification. So we're able to track people in 3D. So this is some more tech that's actually specifically looking for people-shaped things in the laser data. So you can see these blue boxes here are all being drawn around people, and then maybe you can just see in front of the people there's like another red lightsaber just in front of them. That's showing us what sort of trajectory the person is following. So that's kind of important for us, because if we're heading towards a crowd of pedestrians in Greenwich, we need to figure out which way they're going, which way they're going to be heading, and then that helps us understand whether we're going to collide with them or whether we need to avoid them. We also use a lot of tech that is, again, camera-based. So trying to address this question again of what's around me, we have a lot of software that works just with video. So here we are detecting things like cars and cyclists on the roads of Oxford. You'll probably see this in quite a lot of places these days. It's becoming quite common. So we do this using lasers or using vision. And we also have a lot of stuff that would do things like detect pedestrians. So top left is pedestrian detector work in Milton Keynes. Bottom right, that's an AI software. It's actually in the process there of learning what pedestrians look like and what cyclists look like. So the self-learning software is becoming more and more important and more common. And the way that things self-learn is that you have to show the system what, say, a person looks like. People come in all sorts of different sizes and shapes, and you can look at them from all sorts of different orientations. So it takes an awful lot of data to train a system on how to detect a person. So what we do is we probably train the system on maybe a couple of thousand views of people from different angles, different orientation. And the way that the system learns is, as it drives down the street, it's sort of looking out for things around it, and it might think, there's a thing there, I don't recognize where it is, it's a bit closer, I don't recognize where it is, and then a bit closer and say, hey, I recognize that's a person now, which means that all of these other views I saw of that same thing, that was a person as well. And that's the way these systems train themselves, that's the way they learn about the environment. And if they spot a thing that they think is a person, and it's a person here, a person there, and then it flies over the top of the car, then they assume, okay, all of those things I saw can't have been a person, because I know that people don't live in the air, they live on the ground. So you'll find a lot of these systems are coming in now that learn about the environment, learn about the objects, and they teach themselves. So overnight our systems dream. They dream about the data they've seen during the day, and they upgrade their programming and update their capability to work in an environment. And what you will find is that all of this type of training is really specific to the environment we're in. So this particular data set now has been really finely tuned to work in Oxford. It probably wouldn't work anywhere near as well in New York City. It becomes very, very specific to the environment you're in. And we also use the same tech to do things like traffic lights. So behind this vehicle, there's some traffic lights. See where those orange boxes are in the back of the car? That's where we know, that's where they are. So we've been through this data set. Our vehicle's dreamt about traffic lights because we've taught it what traffic lights look like. And it's tagged where they are in the data. So here there's another set of traffic lights hidden behind the vehicle. You can't really rely on your autonomous vehicle spotting traffic lights. I mean, you've really got to know exactly where they are in the real world. And then when you get there, you've got to be able to see them and check that they're green or red or whatever color you need them to be. So again, having this type of capability of being able to learn about the world really simplifies the task of making autonomous. So we've been through where am I? We've been through what's around me. The next step is really what happens next. So the area of what we call trajectory planning is the most complex area. We're taking an awful lot of data. It's really quite hard to explain at this level. So this is one of our vehicles being driven around Oxford, I think. The trajectory planning is really quite complex. But let me explain it in a different way. So here's some artificial intelligence software, just as a sort of a bit of a vogue topic at the moment. This is some software that's been trained on a data set, and it's now driving through Oxford. And in fact, our new office is just down the street on the right there, as it happens. So this is software that's been trained on how people drive. And so in this bottom image here, green is where people would normally drive. The red is where people would normally not drive. So you can see there it's detected there's some things that it can't drive through, which happen to be pedestrians. The thing with artificial intelligence software, it doesn't know they're pedestrians, it just knows that, or it's learned that they are things that people wouldn't normally drive through. And you can see through here that it's quite cleverly figuring out where you might drive. It's not really following the white lines, although that might be part of its programming. And you can see it's not trying to head into traffic, it's really trying to follow a road. And so I think a little bit further up here it comes across some more vehicles and some roadworks, and it figures out it can't drive through them. So a lot of people are really excited about artificial intelligence type software because it appears that just by showing some software where people would drive, you immediately get this trajectory projected, which might be something you can follow. We have different opinions about the science behind that, but we very definitely use this type of output to help us confirm the trajectory we've chosen using more scientific means. That seems to work on the face of it. And the final thing I was going to mention, just very quickly, fleet management. This is one of our maps of Greenwich. We're running in Greenwich a system we developed called Cesium, which is a fleet management tool that's helping us manage many different vehicles down there. And so when you start to operate pods like we have with Harry and the next 5 or 6 vehicles that might be coming along later this year, in this tight environment, we need the vehicles to be communicating all the time, so that if there's 2 vehicles on the same stretch of track, one has to give way to the other. We don't want sort of Mexican standoff with both vehicles trying to edge past. So they have to talk to each other. They have to communicate through the cloud to say, it's your turn to stop there while we go past. And so we've created quite a complex system in Cesium to help us manage those types of vehicles in Greenwich and make sure that they zip around. And it also then lets us start to interface to something like a smartphone app, so we can call the vehicles and have them work as an on-demand transportation form. So I look forward to taking your questions in the Q&A session. Thank you very much for your time.